Right. For ionic equilibrium revision, what all things we should know? First thing we should understand are electrolytes. Electrolytes. Electrolytes means anything which will ionize in ionize in solutions. And preferably these solutions which we are talking is aqueous solution. So these electrolytes can be categorized into two forms. One is strong electrolyte, the other one is weak electrolyte. Strong electrolyte means 100% ionization, so up to 100% ionization. Here it is 1 to 5% ionization, which means it is not getting 100% ionized in solutions. These are weak electrolytes. Again, these electrolytes which in aqueous solutions, in if we compare that in aqueous solutions, we will come across three different type of it. One is acids, then we have bases and salts. These are three types of electrolytes we will be studying in this topic. So to learn these electrolytes, first we should know how do we define this. So it is all about, definition definition of acids, bases and salts. Okay. And see, there are multiple definitions. I'm not going into, each small one of that. Let me put something which is very orally. Arrhenius acid base theory, which means uh, if an electrolyte is able to increase the H plus ion concentration in aqueous solution, we call it as Arrhenius acid. Or if the electrolyte is increasing OH minus concentration, we call it as Arrhenius base. And a product which is forming out of acid base reaction is called as salt. Simple. This is a basic definition we should know. One important definition which we should learn is Bronsted Lowry acid base theory. Okay. Now, here, when it comes to Bronsted Lowry acid base theory, acid in a way is defined as proton acceptor. Anything which will accept proton means H plus. If it accepts an H plus, that is Bronsted Lowry base. And if it is a proton donor, that means it is donating a proton into the solution, then that is Bronsted Lowry acid. Okay. And generally, what you need to know is that an acid, when it reacts with a base, will always give you a conjugate base. That means after removal of H plus, the remaining part is called conjugate base. And base will give you a conjugate acid. In simple terms, if you have HCl added with water and HCl is giving away H plus, it will become Cl minus, and H2O is becoming H3O plus. So HCl and Cl minus, these two are called conjugate acid base pairs. These are conjugate acid base pairs. And the same logic goes with water and H3O plus also. These two will be conjugate acid base pairs. Okay. So given any example, you should be able to figure out whether they are conjugate acid base pairs or not. Conjugate acid base pairs. For example, if I take HCl and Cl minus, yes, this is the one. If I take, H2SO4 and HSO4 minus, yes, this is the one as well. But if I take H2SO4 and SO4 2 minus, then I would not call this as a conjugate acid base pair. Conjugate acid base pair should be immediate H plus releasing or immediate H plus accepting. So if you have ammonia and NH4 plus, so yes, this is conjugate acid base pair. Now you can write the same in terms of the base also. For example, if I have NH4OH and NH4 plus, so that is also a conjugate acid base pair. If you have AlOH thrice and AlOH4 minus, this is also a conjugate acid base pair. So instead of accepting H plus, now it is accepting OH minus. So that way also you can say this one is acting like an acid and this is its conjugate base. Got it? So you can notice that we can have a lot of conjugate acid base pairs like this H3O plus and H2O. I can say NH2 minus if it is becoming NH overall 2 minus, that is also a conjugate acid base pair. If you have H3PO4 and I have H2PO4 minus, that is also a conjugate acid base pair. These are all conjugate acid base pairs. The next point you need to remember from Ionic is that a strong acid, or a strong base can easily give, okay, weak conjugate base or acid, weak conjugate base or acid. But a weak acid, or a base, okay, cannot give strong conjugate acid and strong conjugate acid and base forms. Example, if you notice, if I take Cl minus plus H2O and I'm expecting this to pull off as HCl and OH minus, this does not happen. So this reaction does not take place because this is a weak base. This is a weak acid. A weak base converting into a strong acid, that is not going to happen, or weak acid converting into a strong base, that is not going to happen. But the reverse is true. That is, if HCl is taken with OH minus and this side, the reverse reaction is definitely true. Okay, just a second. Right. So the reverse does not work better. Now, one thing we must know is that list of what is the list of strong acids so that they can convert into weak bases and vice versa. So if you compare the strong acids that include HCl, HBr, HI, don't do that. And then we have HNO3, got it? Just a minute. We have HNO3, H2SO4, HClO4. These are the ones which you should definitely remember, which are very strong acids. These are direct acids. But the ones which are coming from a weak conjugate, weak base, they can also be strong acids. For example, H3O plus, or if you have NH4 plus, got it? Like this, or ROH2 plus from an alcoholic point of view. So these are all going to be strong acids. Okay. Likewise, if you have to compare weak weak acids now. If you compare weak acids, we have a lot of them that include HCHF and HCN, H2S, got it? All phosphoric acid for that matter, H3PO2, H3PO3, H3PO4, and then H2SO3, HNO2, all carboxylic acids are COH, alcohol, okay, phenols, if I take phenolic groups, water or acetylene are C triple bond CH this way, right? All of these are, weak acids. Now, just by watching that, we can actually figure out what are the bases, strong bases. Even ammonia, for that matter, is a weak acid. So if you compare the strong acids, all you need to do, strong bases, all you need to do is write the conjugate bases for them. So what are all the conjugate bases here? That includes F minus, Cn minus, S2 minus or HS minus, then H2PO2 minus, got it? H3PO3, and H3PO4 is a triprotic acid, which means you can have H2, sorry, here, let me rewrite H2PO3 minus, or I can write this as H2PO4 minus, or I can write HPO42 minus, or PO43 minus. All of them are very uh, strong bases which are coming from weak acids. And then we have, HSO3 minus, NO2 minus, RCO minus, RO minus, PHO minus, OH minus, RC triple bond C minus, and NH2 minus. In fact, H2 can also be added as an acid, which gives you a base which is H minus, a very strong base. Got it? And for that matter, if you have any alkane also, which is extremely weak acid, that can be converted into conjugate base, which is RCH2 minus. So these are all strong bases. And lastly, if you compare the list of weak bases, they can directly come from the top here. That includes, Cl minus, Br minus, I minus, SO4 2 minus, ClO4 minus, even H2O or ammonia. Ammonia and water will have the both acid and base property. Got it? And we have ROH, which can be taken as weak base. Amines can also be taken as weak base, and these are the cases. Okay. So I want you to just go through the list once, understand in which case they will act like strong acids, strong bases, or weak acids and weak bases. Because this logic has to be developed in you, that in which case we should consider whether it is a buffer or hydrolysis. For that, you need to have a sound idea about the compounds, whether they will act like acids or bases, and which kind of acids and bases. Now, few important exceptions that you need to remember is, in the list of weak bases include pyridine also, and that pyridine can also become a strong conjugate acid once it takes H plus. So this way, this is going to be strong conjugate acid. Clear, everybody? This list you need to understand. If there is any problem, you can ask me. Samyak, yes, beta.
सर HS माइनस H2S का कॉन्जुगेट है
Yes, बेटा. देखो,
और
दिस इज ए
S2
कॉन्जुगेट.
माइनस
हाँ, HS माइनस है ना. अभी एक बार
यस सर
पॉलीट्रोपिक करता हूँ. ठीक है, इसके नीचे लिख देता हूँ. राइट.
यस
सी, in case of polyprotic acids, what does that mean? For example, अच्छा एग्जाम्पल लेते हैं H3PO4, है ना. And H3PO4 is becoming H2PO4 minus. It is becoming HPO4 minus. Now, as an acid, it can give one H plus here. This can still give one H plus. This can still give H plus. That means all three are acting like acids. This HPO4 2 minus. Within these acid cases, you know that H3PO4 is a weak acid, correct? H3PO4 is weak acid. Now, from that weak acid, if you remove one H plus and you get a negative charge, from this negative charge, pulling H plus becomes even more difficult because H plus will instantly attack that negative charge and try to go back. That's why creating H2PO4, I mean H2PO4 minus acting like an acid is very difficult. On top of that, HPO4 2 minus acting like an acid is even more difficult. So what I can say, this will become a weak acid. This will become even a weak acid. So if you compare the acidic strength, right, I can say that this is how the acidic strength varies. And now comparing the basic strength, see that means after releasing H3, 1H plus, you'll have H2PO4 minus or HPO4 2 minus or PO4 3 minus. Now, from a weak acid, you are generating a conjugate base that has to be strong base. And from a strong base, I mean, you can see this is a very weak acid. So this should become even very strong base. And top of that, if this is a much weaker acid, that should make this as a much stronger base. So this is a very strong base compared to this one. So this becomes the basic strength for that matter.
Yes, sir.
Okay, beta?
Yes, sir.
Is this logic clear? The same thing goes what you said right now. H2S is a very weak acid and HS minus will become even weaker acid while HS minus is a strong base but S2 minus will become even stronger base. So Mac, is that clear beta?
Yes, sir.
Right. This is the case what you need to understand in polyprotic acids and bases. Okay. Now one thing you must have understood that how the equilibrium exists in these cases. Okay, see, let me write down that. Let me put it as an example first. Suppose I have RCOOH, a carboxylic acid, and I'm expecting that in water, right? As soon as you add it in water, it is acting like an acid, so it will give you conjugate base, and this should take H plus away. So this is what it should get. So this is a weak acid. This is a weak base. So it is giving a strong conjugate base and it is also becoming a strong acid. So equilibrium will mostly be lying on the backward direction. That's why whenever you have a weak acid or a weak base added in water, the equilibrium constant value itself will be much lower because most of the time the reaction will be on the backward direction. And this equilibrium constant, if you're writing it for an acid, we call it as Ka. And generally, for weak acids, Ka value is always lesser than 10 raised to power of minus 3. And same goes with base also. For example, if I have NH4OH in the aqueous solution, right? And that if at all I let it dissociate here in the form of NH4 plus and OH minus. So NH4OH, I can write it separately also as ammonia plus water, or I can directly write down. So this is a weak base which is giving a strong conjugate acid and this is a strong base. That also suggests that Kb, which is called the ionization constant of base, will also be less than 10 raised to power of minus 3. That's the reason, guys, whenever we have weak acid, weak bases, we say they exist in equilibrium and the equilibrium is always in the reactant side. Okay, just a second. So the equilibrium always drives on the reactant side now. Okay. So now, in case if I want to figure out how do we calculate the Ka value, let me start with a simple acid here. Okay. For example, if you have Ha, I will call that as an acid. And if it is a weak acid, I'll expect this to ionize into H plus and X minus. So I will say the equilibrium constant associated with it is called dissociation constant for acids, and Ka will be equal to H plus concentration into X minus concentration upon Ha. Okay. And if we consider like this happening at initially at C naught concentration, and as it reaches equilibrium, there is some small amount of dissociation which I can write in terms of alpha. I'm sure everybody understand how to figure out and write the alpha value. Alpha is called as degree of ionization or dissociation. Degree of ionization or dissociation. So if I write that, I can say that K value would be equal to C naught alpha whole square by C naught minus C naught alpha, which makes it C naught alpha square by 1 minus alpha. And most of the cases, alpha value will be less than 0.01 in most cases. So as long as you have alpha less than zero point 0.1, so we can say alpha can be far less than 1. So we can ignore that. So I can write Ka value as simply C naught alpha square, ignoring the alpha in the denominator. Hence, alpha can be figured out as Ka upon C naught. So from here we can say as the concentration decreases, which means it is about dilution, then alpha value will increase. That is about dissociation. So dissociation increases over the dilution. This principle is called, you know, Oswald's dilution law. Got it? And once you know how to write the alpha value, we can figure out what is the H plus concentration as well. H plus concentration is equal to, C naught alpha, which can be written as under root of Ka C naught. Okay. If I take minus log on both sides, that is minus log of H plus concentration is equal to half of, minus log of Ka and minus log of C naught. Now, minus log of H plus concentration is what we, call that as pH. And that is equal to half of, that minus log of K is what we call it as pKa minus log C naught. So which means if it comes to weak acid, the pH calculation can be used by this formula. In most cases, it will satisfy as long as alpha value is less than 0.01. Got it? Now, since I have done it for weak acids, the same logic can be applied even for weak bases. So which means if you take it for weak bases, okay, so for weak bases like BOH for that matter, BOH aqueous, then POH in such case, the formula would be POH will be equal to half of PKB minus log C naught. This is what you would get it as, you know, weak basis. Okay, right? So this is the first part you need to understand how we are relating acids in terms, mathematically how we are relating with formulas. Second, if you have only aqueous solution, there are few important tips we must know. In case of aqueous solutions, aqueous solutions, there are three types of solutions here. One is neutral, which means where the H plus concentration and OH minus concentration in the aqueous solution are equal. In that case, we can say the H plus concentration into OH minus concentration typically will be equal to a constant which we call it as Kw, and which is 10 raised to power of minus 14 at temperature being 25 degrees Celsius. Okay. Now, the same will be Kw, but 10 raised to power of minus 13 at temperature being 83 degrees Celsius, which suggests that as the temperature is increasing, the ionization increases. In fact, all ionic equilibriums are endothermic. That means they will take the energy, they'll take the heat and dissociate further. Okay. So we can say that for a neutral solution, the pH value plus pOH value will be equal to 14. And since pH and pOH are equal, I can say pH has to be equal to 7 if it is at 25 degrees Celsius, or pH plus pOH is equal to 13, and pH has to be 6.5 if you are operating at around 83 degrees Celsius. Okay. By default, everything which we do it is at 25 degrees Celsius. This is about neutral solution. Okay. Now, what if you have an acidic solution? In case of acidic solution, we assume that the H plus concentration is greater than OH minus concentration, correct? But the product of these two should always remain same, which means POH plus pH has to be equal to 14, and in that case pH has to be less than 7 at 25 degrees Celsius. Okay, just a second. Right, sorry. So pH has to be less than 7. Similarly, if it is a basic solution, we expect the OH minus concentration has to be greater than H plus concentration, and POH plus pH has to be again 14, and this is all operating at 25 degrees Celsius. But we can say that pH has to be greater than 7, or POH has to be less than 7 in that case. Okay. So this is the briefing you should know about, aqueous solutions, how they behave in aqueous solutions. Different solutions behave in aqueous solutions. Okay. Secondly, suppose if you have an acid like HX, and you know that for HX, its ionization is H plus X minus aqueous. Clear? And this is Ka. So what will be the Kb for X minus? Because X minus is a base now. It can accept H plus from water and convert itself into HX plus OH minus. So that's how it can become conjugate base here. So this will be Kb value. Okay, Kb of the conjugate base. What you will find out that Ka value is equal to H plus into X minus concentration by Hx, while Kb value will be Hx into OH minus concentration upon X minus. So if you multiply both of them, Ka into Kb, you will find out it is basically a product of H plus and OH minus, which is nothing but Kw. So therefore, for a conjugate acid and base, remember Ka multiplied by Kb value will be always equal to Kw, or pKa plus pKb of conjugate acid base pair will be equal to pKw. Okay. So this is the next important formula we should remember, that how the pK values of uh, different acids and bases are related with each other. Done with it. Now, have you noticed something? When it comes to acid here, if the Ka value is directly related to H plus concentration, you will call an acid having more H plus concentration is stronger, correct? For the same composition, let's say if I take 1 mole and I get, you know, a lot of H plus ion concentration in it, so then I'll say it is a stronger acid, correct? Like that, if I compare two monobasic acids, the strength of acids is defined. See, check out next point here is strength of acids. Strength of acids is compared based upon H plus concentration. Suppose H plus of HX1 is greater than H plus of HX2 for the same concentration, for same initial concentration. Okay, then we can say HX1 is stronger acid than HX, sorry, than HX2, which means if I compare H plus formula is what beta? C naught into alpha 1, correct? That divided by C naught into alpha 2. If I take the ratio of H plus concentration of first one and H plus concentration in the second one, this is what I should get. And you know that this can also be replaced as under root of Ka C naught 1 by under root of Ka2 C naught. So that is equal to under root of Ka1 by Ka2. So this will be the strength of acids. This is how you relate the strength of acids. So under root of K1, K2 will be called as the strength of acids or the comparison of acids. Now from here you can clearly notice that if a Ka1 value is greater than Ka2, then also I can call that, then also I can say that HX1 acid is stronger than HX2 acid, which implies if you have pKa1, because pKa1 will be reverse of it. So pK1 will be less than pKa2, which also implies HX1 is stronger acid than HX2 in terms of strength. So remember, the higher the pK value, lower is the acidic strength. That's why if you compare pK value of methane, which is 48, pK value of ammonia, which is 38, okay, pK value of phenol, which is 10, and pK value of, carboxylic acid, which is generally around 5. So therefore, if you compare the acidic strength here, it's pretty much clear that RCOOH is a stronger acid than phenol, then ammonia, then CH4. Correct? So this is another way of comparing the strength just by understanding the PA values or pK values. Clear with this logic, everybody? Next. The next important point what you need to learn is how do we calculate the pH of the solutions. Okay. Now we will take case by case. Now here I would suggest all of you to work out along with me. Okay. So I want all of you to work out. Please open pen and book with you. We will do it like questions, and we need to understand how do we need to solve this kind of cases, each cases, right? So please note that first case 1. Case 1 is when you have a strong acid and a strong base reacting with each other. Got it? So I'll write down the question, you do it together. Let's see. Suppose I have 800 ml of 0.1 molar 1 molar NaOH, okay, treated with 200 ml of 0.1 molar H2SO4. You don't have to write the question, just understand that and solve it along with me. Okay. Find pH of final solution. You need to find the pH of final solution. Okay. So check this out, how we can do it. Notice one by one every First, you have to learn to write the balanced equation, which is very, very essential for these cases. 2NaOH plus H2SO4 is giving Na2SO4 plus 2H2O. And now you can see 800 into 0.1 are the number of millimoles. So I got 80 millimoles. Here we have 200 into 0.1, which makes it 20 millimoles. I already kept a balanced equation. You can see for every 2 moles, 1 mole is required. For 80, you require 40, but 20 is given, which means this will become a limiting reagent. This is the excess reagent. So limiting reagent always get completely consumed. So which means for every 1 mole, we require 2 moles. So 20 moles require 40 moles. So subtract that 40. So which means 40 millimoles left. This many millimoles are left. And on the other hand, when you have H2SO4 getting completely consumed here, so 1 mole is giving 1 mole. So 20 millimoles will give you 20 millimoles of salt. 20 millimoles of salt. And rest is water. We are not worried about that. So basically, you need to check out which one is in the limiting excess amount. And based on that, you should know how to calculate the pH. So check out. We know that now NaOH is going to be left over in the solution along with salt and water. So being a strong base, it will ionize completely, which means this 40 millimoles will also be consumed into, all of that will be consumed into 40 millimoles of this and 40 millimoles of OH minus. So now calculate the concentration of OH minus, which is equal to 40 millimoles divided by total volume. Total volume is 1000 ml. Okay, so that makes it 4 by 100. So the pOH value is equal to log of 100 minus log of 4, which is equal to 2 minus 0.6, which is 1.4. So if pOH is 1.4, then the pH value will be equal to 12.6. So that is what is expected out of you to calculate the pH of the solution. If anybody has a problem with this question, any problem in understanding, they can please ask me right now, or else I will go ahead. Keep doing along with me. All good? Tanish, any doubt with this case, beta?
Yes.
Ayushi?
No, sir.
Sudiksha? Sudiksha, please respond.
No, sir.
Right. So if you have done this case, let me pull up the next case with the same thing, same logic. Let me put this as case 2, everybody. So in this case 2, the only thing I'm changing here is 400. Okay. So now that volume has changed to be 400. Okay. So the calculation wise, everything, I mean, the equation wise, everything looks similar. So I'm just copying it. Correct. You can rewrite that. You can rewrite the equation, no harm in it. So just change the conditions now and see what would happen. So here we had, H2SO4 was given. So which means we had 400 into 0.1, which is 40 millimoles. You know that 2 requires 1, so 80 requires 40. So that means it is in an equal amount. So there is no limiting here. Both of them are in exact amount. So in that case, only salt and water is formed. In the case of only salt and water formed, you will notice that the final H plus concentration and OH minus concentration will be equal. In case of salt coming from strong acid and strong base combination, then pH value will be equal to 7. So this solves the second case, that is when pH is equal to 7. Okay. So Third case is when this will become limiting in terms of base. So I'm taking the third case now. Now third case is I'm just changing this to, 400 and 400. So now you have 400 ml of and 400 ml of this one. Okay. Now again the logic would be the similar thing. So we have 2 NaOH plus H2SO4, in which this is 400 into zero point 0.1 and this is also 400 into zero point 0.1. So this one is 40 millimoles and this one is 40 millimoles as well. Both of them are giving Na2SO4, right? So I'm not writing anything further to it because you can clearly make out that these two, sorry, in this case, NaOH is now limiting. So only 20 millimoles will be consumed here. So 20 will be remaining. 20 will be remaining. So in that case, you can see H2SO4, if you have H2SO4, it will turn out into 2H plus SO4 2 minus. Got it? And you have this 20 millimoles here. So that would get completely converted into, 40 millimoles of H plus. And H plus concentration will be equal to 40 divided by total volume. In this case, the total volume is 800, right? So that makes it 1 by 20. So pH will be equal to log of 20. So which is equal to 1.3. So that would be the pH of the solution. Clear? So this is the first type of questions where a strong acid, strong base combinations are given. We just have to simply identify pH. Okay. I'm assuming all of you are comfortable with this kind because these are all something which you are primarily learned in stoichiometry already. Now let's get into the next case one. Again, next case here. So case 4, where you have a weak acid and a strong acid combined. Weak acid and a strong acid combined. So let us again put this as a problem and see how this can be made. So 500 ml of 0.1 molar CH3COOH, correct? You know, is added to is added to here 1 ml of 0.1 molar, sorry, 0.1 molar, sorry, 1 molar, 1 ml of 1 molar H plus ion concentration or 1 molar HCl, 1 molar HCl. Find, you know, pH of final solution. pKa value is given as 4.8 or Ka value is approximately given as 1.8 into 10 raised to power of minus 5. You can take anything that is required in the question. Now, let's see how we can solve this. In such case, there is a concept of common ion you have to use. Now, notice CH3COOH aqueous is ionizing into CH3COO minus and H plus. Correct? Initial concentration here, let this be C naught, and I'll put this in terms of number of moles. So I have 500 into 0.1 molar initially. Okay. Initially, this is the concentration I have. But already there is an H plus ion concentration which is 1 ml into 1 molar. Correct? 1 ml into 1 molar is already present. Let's just make some Minecraft. 1 second. Sorry. So these many millimoles we have. Here also we have these many millimoles. Correct. So if apparently if you notice that I had initially 50 millimoles and we have 1 millimole already present in the solution. So out of which we can say out of 50 some x millimoles have been consumed here to form x and 1 plus x here. And then I can write Ka is equal to x into 1 plus x divided by 50 minus x. Got it? Now listen up. Due to the common ion effect, the x value will be drastically low because as it is, x is very small amount. On top of that, there is already a common ion because of which the dissociation will be low. So we can say that Ka value will be equal to x into 1 plus x divided by 50. Okay. Now listen, in most JE cases, in JE mains cases, here you can write Ka directly as x into 1 divided by 50. That means you are ignoring this x as well. Okay, on the numerator also you are ignoring. But in here, in JE Advanced, when you are using these cases, my suggestion is first try to work out on the quadratic equation and see. So it is x square plus x divided by 50 is what I have. So from there, I can say x square plus x is equal to 1.8 into 50 into 10 raised to power of minus 5. This is what we have. So from here, you can solve it for x again. Now, most of the cases, you will notice that the x value is very, very smaller as compared to that of value of 1. Okay. Let's assume, okay, because I'm not solving completely. Let's assume this one is coming close to 10 raised to power of minus 3. Okay, after all the solving, it is coming as 10 raised to power of minus 3. So in that case, what is the H plus concentration overall? Overall will be equal to 1 plus X. Okay, 1 plus X is the overall amount. So that should be equal to 1 plus 10 raised to power of minus 3 millimoles. Sorry, this is moles, okay, not concentration. H plus moles. Now, what will be the concentration of H plus ions now? In that case, if I ignore that 10 raised to power of minus 3, it will be simply 1 by total volume. Total volume is 500 plus 1, but this 1 ml can be ignored. So divided by 500. Okay, so therefore, pH will be equal to log of 500. So which is 2 plus log 5, which is 0.7. So 2.7 will be the approximate pH of the solution, which means weak acids hardly influence the H plus concentration or H plus amount or H plus moles which a strong acid is providing. Case 4 is clear, everybody? Any doubt here? Right. Let's check out case 5. Case 5 is when you have a weak acid and another weak acid is been added. So this is weak acid 1 plus weak acid 2. So in such case, let's say I have HA acid of Ka value, Ka given as Ka1 and concentration given as C1 and HB here, sorry, sorry. So HA acid of, HB, another acid, HB, the Ka value, let this be Ka2 and concentration C2. If you mix both of them, I'm directly writing the equations, everybody. So check out Ha ionizing into H plus A minus, HB ionizing into H plus and B minus, If this is C1 minus X concentration, this will be X and X. This will be C2 minus Y concentration. This will be X plus Y and Y. Here also it will be X plus Y because it is a common ion. So the contribution happens from both the ends. And this is Ka1 and this is Ka2. Now using this finding of K1 and Ka2, we can write H plus concentration, which is equal to X plus Y, is equal to under root of Ka1 C1 plus Ka2 C2 directly. Okay. So please make sure that you directly use this as a formula. Got it? Instead of worrying it something, you can directly use it like a formula. Done. So in the case of weak acid, weak base, I request all of you to remember it like a formula. It is under root of K1 C1 plus K2 C2. Okay. Next. Let's talk about case 6. Case 6. Case 6 is extremely, extremely weak acid concentration. Sorry, extremely strong acid concentration. Okay. Extremely low concentration. Extremely low concentration of strong acid. That's how I need to write down that. Extremely low concentration of strong acid. We'll do with an example. Suppose if HCl concentration is given as 10 raised to power of minus 8, then find pH of aqueous solution. Now, for such a low value of HCl, low concentration of HCl, you cannot simply say that the H plus concentration is 10 raised to power of minus 8, which is coming from HCl, and pH is 8. So now that will become wrong here. Got it? Because whenever you are measuring H plus, it should be about H plus of the solution. And in solution, water is always present. And relatively, now the water is sufficiently contributing because in front of HCl being 10 raised to power of minus 8, I cannot ignore the water's dissociation. So if water, which is having originally some concentration, but now because of HCl, it has 10 raised to power of minus 8 initially. Now what happens? There will be some amount of ionization from water, which is 10 raised to power of minus 8 plus X and X. So that if you take it into account, you can write Kw as X into 10 raised to power of minus 8 plus X, which is equal to 10 raised to power of minus 14. So if you calculate this X, that will come somewhere close to that of, minus 8 or something like this. Sorry, minus 7 or something you will get. Got it? Which means if I add these two, then I get H plus concentration. So H plus concentration of the solution will be equal to this 10 raised to power of minus 8 plus 10 raised to power of minus 7 approximately. You will get that as 10 raised to power of minus 7. I'm writing it approximately. So which means this is 10 raised to power of minus 7 into 0.9, correct? That is how much, sorry, I'll write it this way, 10 raised to power of minus 8 into 10, correct? I can write that because this 10 raised to power of minus 7 can be written as 10 raised to power of minus 8 into 10 plus 10 raised to power of minus 8. So you can write this 10 raised to power of minus 8 into 11. This will be the concentration. So therefore, pH will be equal to 8 minus log 11. Log 11 is slightly greater than 1, right? So that means it is 8 minus something like 1.001 like that, correct? So that makes it 6.996, which is still less than 7. So that's how the pH value will always remain less than 7 for an acid, irrespective of how low the concentration is. Got it? This is case 6. I hope all of you got that. If any problem, you can ask me now.
Sir, X is in moles, right?
No, concentrations. Everything I have written is in concentration.
Okay, sir.
Hmm. Right. Now let's talk about buffer solutions. To understand the buffer solutions, one must know that there are two types of buffer. One is acidic buffer, basic buffer. Of course, there are neutral buffers also. I will do it through the problem solving, so don't worry about it. So let us focus more on the important part of the theory, acidic buffer. Acidic buffer means our expectation is there must be a weak acid along with its conjugate base salt. So if you have this combination, then we say acidic buffer is present. See, first thing is weak acid. So let us put some examples. HCl, a weak acid. And if I take this as barium cyanide twice, which means barium hydroxide is a strong base. After reacting with this, we will get a salt which has a conjugate acid, cyanide, conjugate base. Fear minus is a conjugate base. So yes, this is a buffer solution, acidic buffer. Likewise, if you have H3PO4 and I have NaH2PO4, that is also a buffer. And if you have H2CO3 and NaHCO3, that is also a buffer. Or I have, KHCO3, and I have Na2CO3. This is also a buffer because HCO3 can be considered as a weak acid and CO3 2 minus can be considered as a conjugate base. Okay. So again, this is also an acidic buffer. If at all I take HCl plus NaCl, can we consider this as a buffer here? No, because HCl is a strong acid. Likewise, if you have H2S and I'm treating this with, NaCN, can this be considered as buffer? No, because we have a weak acid, but we do not have its conjugate base. Got it? These are not buffer solutions. Clear? Likewise, you can take any weak acid buffer also, like if you have HF, right? That's a weak acid, and NaF, that's a conjugate base. So yes, this is a buffer. Or any carboxylic acid, RCOOH, and its salt, RCOOK, that is also a buffer. Got it? Or an alcohol, ROH, if you consider it as an weak acid, and you have alkoxide ion, that is also a buffer. So these are all acidic buffers. Okay. In acidic buffer, pH calculation is very easy. Let me show you with an example. Sorry, pH calculation. So if you have to calculate the pH, let me take with an example. Suppose HCl is a weak acid. You know that it will ionize as H plus and Cl minus. Correct? So if this is a concentration A, correct, initially, and now you say some X amount is lost here, X amount has formed here. But what if you already have a barium cyanide here, barium cyanide, correct, which is giving Ba2 plus 2Cn minus. If this is salt concentration, so this will become S and 2S, correct? So that means now this equilibrium, because of the presence of barium cyanide, has changed where you have X plus 2S as the concentration. This will become X plus 2S concentration. Okay. Because of which now the ionization, the X value is very small now. Because X value is very small, I can say Ka value is equal to H plus concentration into Cn minus concentration divided by HCN concentration, which is equal to X into X plus 2S concentration, that divided by, okay, A minus X concentration. And because this X is very small, we can always ignore them in both the cases. Hence, Ka value will be simply X into 2S concentration divided by A. Okay. So from here, X is what? X is H plus concentration. So H plus concentration is equal to Ka into A by 2S. Okay. So pH now can be written as pKa plus log of 2S by A. S being the concentration of the salt, but here what it should be salt ion concentration. So therefore, the same formula can be written as a general formula as pK plus log of salt ion concentration upon acid concentration. Got it? This is called Henderson's formula. Henderson's formula. So for buffer, the formula is very simple. All you need to do is identify the buffer solution, right? If it is acidic buffer or a basic buffer, then apply the formula for this. So this is the formula which we are looking for. Then acidic buffer is clear, everybody. Same goes with basic buffer also. For basic buffer, sorry, for basic buffer, clear, we must have a weak base plus conjugate acid salt. We should have conjugate acid salt. Here the examples are very few, like NH4OH is a weak base. NH4Cl is a conjugate acid from a strong conjugate acid of that particular base. Or NH4OH plus, let's say ammonium sulfate, like this, these kind of combinations. So these are all weak basic buffers. Or you can take pyridine also plus pyridinium, pyridinium chloride plus Cl minus, chloride, bromide, iodide, anything. These combinations are all basic buffers. So for basic buffers, pOH calculation will be equal to pKb plus log of salt concentration. Again, salt. Whenever it is salt written, you should understand that it is about salt ion concentration and not just salt. Okay. So this is what you would get in the case of basic buffer. Clear? The next term here we should learn is about buffer capacity. Buffer capacity. Okay. Buffer capacity usually written as eta. So this eta buffer capacity is how much amount of acid or a base that you are adding, right, in moles, correct, to change the pH of the solution, right, delta pH by 1 liter, by 1 unit. So if we are supposed to change the pH of the value, then you know number of moles of strong acid or a strong base per liter of buffer solution, added to change pH by 1 unit. That is called buffer capacity. Clear, everybody? Okay. Now, sometimes if you want to get an idea about buffer capacity or buffer index, this is also called buffer index. So buffer index Bi can also be written as S into A, salt into acid concentration upon salt plus acid concentration. This value also you can check out, which will give an approximate value of the buffer index or buffer capacity. Got it? Usually, you will find that usually when salt concentration and acid concentration is more, the eta value will be higher. That means the quality of buffer is better when the concentration of these two are equal, and generally if they are maintained at high concentrations. If you maintain them at high concentrations, eta value will be higher. Okay. I guess the buffer case is clear, everybody. Next one is about salt hydrolysis. Salt hydrolysis. Salt hydrolysis means, okay, salt ions breaking water molecules. How salt ions are breaking water molecules, that implies salt hydrolysis. Got it? So starting with the first one, if you have a strong acid and a strong base formed salt like NaCl, okay, Ki, K2SO4, NaNO3, clear? Barium chlorate, perchlorate. Got it? Now, if you compare all of these are all coming from strong acid and strong base. For strong acid and strong base, what you will notice that there is no hydrolysis. That means you will not see neither the cation nor the anion has the strength to break water molecules, which implies the pH of solution will be close to 7. So it will be close to 7. See the second case, when you have weak acid and strong base salt, weak acid and strong base salt. Weak acid like CH3COOH, and that is combined with strong base. Strong base is NaOH. So it will become CH3CONa. This is the salt which is formed. Like that, any of the salts are present. Like, Na, if you have uh, NaCl, correct? If you have K2S, if you have Na2CO3, clear? And if you have any monoprotic acids like HCOOK, correct? Or if you have any benzoic acid, let's say, benzoic acid CO minus Na plus, like this. If you see these kind of combinations anywhere, this is coming from a weak acid and a strong base salt. Now, these formulas of salt hydrolysis can be applied only when salt is present, only when salt and water is present. So pH in such case will be equal to, pK, pKw, sorry, half of pKw plus pKa plus log of salt ion concentration. So again, salt ion concentration in this case. This is the formula you would be applying directly. Okay. Now, just to show you with an example what equilibriums that exist and how this formula has been derived, we don't have to derive it, but you just need to know the information of what are the equilibria that were existing. Let me take an example of cyanide, for example. Cyanide, when you keep it in water, it will ionize the water molecule to get into HCN and convert itself into OH minus. This equilibrium constant is called Kh, and if the salt ion concentration initially C naught minus C naught H, which is the degree of hydrolysis, this will be written as C naught H, C naught H, and H will be equal to under root of Kh into C naught. Just like how we write that for alpha, the same logic you have to do it for H here. So we got it Kh here. Kh can also be written in terms of Kw by Ka, and using these two informations you can calculate what is the OH minus concentration. OH minus concentration in this case is C naught H. Now using this information, first again OH minus, if you convert that into H plus concentration, finally equation you will get this is pH like this. Okay, this much information you should know. This is about the second case. Now let's talk about the third case, which is when you have a strong acid and a weak base salt. You have a strong acid and weak base salt. Now, strong acid, something like HCl, HBr, HI, that is where we are coming across. Weak base like ammonia. So that means if you have ammonium chloride, correct, Cl minus, or ammonium sulfate, in this case, we have ammonium sulfate, or anything like a pyridine, right? Pyridinium, pyridinium sulfate or pyridinium nitrate. anything like that. These kind of combinations where you have a strong acid and a weak base salt combined forms. Now, this would give you this particular pH. Now, earlier, one thing you should remember, first let me write the formula, then I'll come back. In such cases, how do we calculate the pH? pH will be simply half of pKw minus pKb minus log of salt ion concentration. This is as per strong acid, weak base salt. Now, one thing you need to remember and realize is that in the first case, you are generating OH minus in the solution. Therefore, the pH value always has to be greater than 7 in the first case. Now, in this case, if at all I write these similar equations, what do we get here? Would be like NH4 plus when you adding it to water, it is giving in this equilibrium constant, it will become NH4OH and generating H plus ion. So that means it is increasing the H plus ion concentration. Hence, in such case, pH value should be less than 7. This is how the hydrolysis is happening. And next, the fourth case is about weak acid and weak base salt. When there is only salt present, but it is coming from weak acid, weak base. That is something like CH3CO minus and NH4 plus. Okay, both of them are weak. Or we have ammonium, NH4 coming NH4 plus and Cn minus. Correct? Ammonium cyanide. So when you have weak acid, weak base salts present this way, right? In such case, the pH value will be calculated as half of pKw plus pKa minus pKb. It's like, you're taking the summation of these two and just trying to erase these two. That will be your pH value. So from here we can say, now we cannot say that pH value will be always equal to or less than 7, less than or equal to 7. It could be on either direction. Okay, it will be on either direction depending upon K and Kb values. Okay. Now here, how does the equilibrium look like? If you notice, CH3 CO minus plus NH4 plus H2O, this is ionizing into CH3 COOH plus NH4OH. So if this is KH here and this is C naught minus C naught H, C naught minus C naught H, and this is C naught H and C naught H, that's why KH will remain 1 minus H whole square, sorry, H square by 1 minus H whole square. So there is no C naught value that is present in the numerator or denominator. So here is an important part, that it is, this hydrolysis is independent of initial concentration. It is independent of initial concentration. This is about KH value. In such case, you just need to know what is the pK value, pKb value, and from there you can calculate the pH value. This is case 4. Next, case 5 is in the case of amphiprotic salt hydrolysis. Amphiprotic means these are the salts which still have an acidic hydrogen left. Like, what are the examples? H2, H2PO4 minus, HPO4 2 minus salts. Okay, HS minus. Got it. And if you have HCO3 minus, like this. These are all the amphiprotic salts. For these kind of amphiprotic salts, the pH value, always depends upon half of pKa1 plus pKa2, right? In case of first dissociated salt ion. That means first H plus has been released, then the salt ion has been formed for this formula. Or for example, for if you have HPO4 2 minus, in that case pH will be equal to half of pKa2 plus pK3. That is the average we need to check off. So for amphiprotic salt, the formula is pretty simple. You just need to uh, check out which type of dissociation it is and accordingly use that. This is for amphiprotic salts. Okay. So just have a quick overview of the hydrolysis formulas, everybody. Check out 2 to 5. These are the hydrolysis formulas. Then we'll go ahead. Suppose if you have an polyprotic acid like H3PO4 बेटा, ठीक है, अब ये फर्स्ट टाइम डिसोसिएट होने के बाद H2PO4 माइनस बनेगा, ये फर्स्ट वाला सॉल्ट केस है। अगर ये डिसोसिएट फिर से हो रहा है HPO4 2 माइनस, ठीक है, तो ये सेकेंड वाला सॉल्ट केस है। अगर ये डिसोसिएट होके PO4 3 माइनस बन रहा है तो ये थर्ड वाला केस हो गया। देखो तीनों केस में कैसे पीएच कैलकुलेट करना चाहिए मैं बताता हूँ। फर्स्ट केस में पीएच विल बी सिंपली हाफ ऑफ pKa1 प्लस pKa2। ये जब ओनली सॉल्ट होगा तो ये यूज करेंगे आप फॉर्मूला। ओके बेटा। सेकेंड केस
Yes.
में पीएच हाफ ऑफ pKa2 प्लस pKa3 ये यूज करेंगे। थर्ड केस में नाउ दिस इज ए नॉर्मल सॉल्ट है ना। नॉर्मल सॉल्ट का हाइड्रोलिसिस फॉर्मूला हमने लर्न किया है, दैट इज इक्वल टू हाफ ऑफ pKw प्लस pKa3 because now it is about third dissociation plus log of C naught. Done.
Okay, sir.
Is this clear?
Yes, sir.
So depending upon the type of salt, which salt you are talking about, वो वाला dissociation करना चाहिए. Okay.
Okay, sir.
Is in the case of polyprotic acids and bases. So first let us say polyprotic acids. Let's calculate for polyprotic acids. Okay. Most of the time, diprotic acids are asked for you. So diprotic cases. Okay. The first case will be like I have H2S, concentration C naught given and Ka1 and Ka2 given. We need to find HS minus concentration and S2 minus concentration. This is typically the question. Very straightforward question. So in this case, what we do? We have H2S ionizing as H plus and HS minus. You'll write it like this: C naught minus X, X and X, and on the other hand, HS minus is also ionizing to give H plus and S2 minus. So this is Ka1, this is Ka2, and from X some Y amount is lost. So this will become X plus Y and Y. Here it will become X minus Y and X plus Y. Okay. So we could write this, we can write it in these two ways. Clear? Now, what can I write about Ka1? Ka1 will be equal to X plus Y concentration into X minus Y concentration by C naught minus X, and Ka2 will be equal to X plus Y concentration into Y concentration by X minus Y concentration. In all our questions, please remember C naught value will be way higher than X and X is way higher than Y. So that's why we can ignore X here, Y here, Y here. We can ignore Y here and Y here. That's why you will get Ka1 is equal to X square by C naught, while Ka2 will be equal to Xy by X, which is equal to Y. So this is the first case, everybody. So you should know how to relate Ka1 and how to relate Ka2. This is the first case. I hope all of you understood that. Because once you know that, you can calculate what is HS minus now. HS minus you can calculate from the first case, which is equal to under root of Ka1 C naught, and S2 minus is same as that of Y, which is equal to Ka2. So this is case 1. I hope all of you are comfortable with this first case. Yeah. Next, second case. Second case is H2S concentration given as C naught. Okay. Uh, H plus, sorry, HCl, HCl of concentration P, P molar is already added, correct? Then find HS minus concentration and S2 minus concentration. In that case, how do we do that? Now, the idea of the equations is still the same. The way we have written, it will still be the same here. But only thing is already there is an HCl present in it. Because there is an HCl present in it, you will not write this x minus y. Instead of writing this as instead of writing this as x plus y and x plus y, you will directly write the concentration given. So you will write this as simply P molar and P molar. Because HCl is a very dominant acid, so you can directly write that H plus to defined have already. Now you can write the K value, right, as Ka1 is equal to P into x minus y divided by C naught minus x, while Ka2 will be equal to P into y divided by x minus y. Now ignore the terms here. X you can ignore, y you can ignore, x, y you can ignore here. So from here, you know that Ka1 is equal to Px by C naught. So x, which is equal to x minus y. X minus y में y को ignore कर सकते हो. So x is what we need to find out. So Ka1 C naught by P. This is how Hs minus concentration will come. And y is equal to Ka2 x by P. X तो हमने calculate कर लिया है यहाँ पर. So you substitute that value, calculate y, and y is equal to S2 minus concentration, right? These are the two cases which are very, very frequently asked to you. So please check this out properly. If there is any problem, you can ask me. Okay, in case of triprotic acid, okay, in such case it is simpler. What you need to do is H3X is an acid. It is dissociating as H2X minus plus H plus, and H2X minus is ionizing as HX2 minus plus H plus, and HX2 minus is ionizing as X3 minus plus H plus. Okay, and now here you can see C naught minus X, 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 and X minus Y, 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 Y minus Z, Z, Z. First write this. Now put the common ions in all the cases. So this will be Y plus Z, this will be X plus Z, this will be X plus Y. While here it will be X minus Y, here it is Y minus Z. Right? These are the factors you should be able to write. And from there, you can write Ka1 is equal to X minus Y into X plus Y plus Z upon C naught minus X. Ka2 is equal to Y minus Z into X plus Y plus Z upon X minus Y. Ka3 will be equal to Z into X plus Y plus Z divided by y minus z. So these are the three paths. And now you know what to ignore. C naught is far greater than x is far greater than y is far greater than z. Ignore them accordingly. Right? So this is about triprotic acids. And lastly, what we have, is about sparingly soluble salts. So if at all we have sparingly soluble salts, then how do we solve the cases? Check. For example, I'll take a simple case like AgCl, let's say AgCl solid. AgCl solid, when it get dissolved in aqueous solution, right? It will have a small composition, and that, let's say, that small composition is called S. S is the concentration, and the dissolved amount of AgCl might mostly ionize, right? Mostly ionize completely. Backward reaction is hardly favorable. So it will be like Ag plus aqueous plus Cl minus aqueous, right? Now it will be giving a new equilibrium, which is AgCl solid, which is in equilibrium with Ag plus aqueous plus Cl minus aqueous. Got it? Which means if I say that initially this was S concentration, now that started ionizing into some alpha amount. So this will become S alpha, and here also I'll write it as S alpha. And what you need to realize in most cases, the salts present in the aqueous solution will ionize 100%, which means alpha is equal to 1. So if alpha is equal to 1, then AgCl solid with equilibrium with, sorry, I'll directly copy this one. If AgCl solid, which is in equilibrium with this Ag plus and Cl minus, now I can say that here the concentration will remain S and S. And that is what we define as solubility product, which is Ag plus concentration into Cl minus concentration, which is S square. That's how we can figure out what is the solubility product. Okay. Now, if you know the solubility product, now what we can do, if you have any example of different forms of salt like this, which is ionizing like this, X moles of M, Y plus Y moles of N, X minus. Now, if you have to write in terms of solubility, that molar, that stoichiometry will also come into the factor. So this will be the value, and Kp value will be equal to X is raised to power of X and Y is raised to power of Y. So that is X raised to power of X, Y raised to power of Y, and S raised to power of X plus Y. This will become the Kp value for a general salt. For any generic salt, this is how we write the Kp value. Got it? Next. In case of common ion, if you have a common ion, effect is observed. Let me show you with some example. Suppose I have a barium carbonate, right, which is in equilibrium with barium 2 plus aqueous plus CO3 2 minus aqueous. And here, let us say this is KSP1 present. And similarly, if you have barium sulfate, and that is equilibrium with barium 2 plus and SO4 2 minus, and this is at KSP2. When both of them are mixed, let's say the solubility here is S1 and S1, here it is S2 and S2. But because of the common ion, here I need to show S1 plus S2. Here also I need to show S1 plus S2. So that makes it KSP1 is equal to S1 plus S2 into S1, and KSP2 is equal to S1 plus S2 into S2. So from here I can say S1 plus S2 whole square is equal to KSP1 plus KSP2. So from here I can get S1 plus S2, which is also equal to barium 2 plus concentration, is equal to under root of KSP1 plus KSP2. That's how we can figure out. So after this, you can calculate the solubility S1 also and S2 also. But this is a common approach how you will do this. The next case is okay. Sparingly soluble salt in buffer. Sparingly soluble salt in buffer. If you have it in buffer solution, how do we solve this? Let me show you with an example. Suppose I have AgCN solid. It is in equilibrium with Ag plus aqueous plus Cn minus aqueous. But if the question is given that this has been added into a buffer solution of pH 3, that means it is in buffer solution of pH 3 means it is in an acidic solution. In that case, what you need to realize is this one. Cn minus will react with this H plus in the solution and convert into HCN. Correct? Why would it do so? Because Cn minus is coming from a weak acid. So it is a very strong base. That strong base will definitely react with H plus to convert into HCl. Now please check this out. Suppose if the concentration of Ag plus is S, which is the solubility form, then Cn minus will be S minus some X amount. Here also S minus some X amount and X amount here. So from here I can say that Ag plus concentration, which is S, should be equal to Cn minus concentration plus HCN concentration, isn't it? And also, the second equilibrium is about Ka value, 1 by Ka value. So I can say Ka concentration is equal to Cn minus concentration into H plus concentration upon HCN concentration. So from here I can figure out what is HCN concentration, which is equal to Cn minus into H plus upon Ka concentration. Substitute this back into the equation. So I'll get solubility S is equal to Cn minus into, Cn minus plus HCl. HCl can be again written as Cn minus into H plus concentration divided by Ka value. And you know that Ksp value at any point of time will be equal to Ag plus concentration into Cn minus concentration. So from here I can write Cn minus concentration, which is equal to Ksp upon solubility, because Ag plus concentration is the solubility. Now let's substitute this value back here. So what would I get? Solubility S is equal to Cn minus concentration, which is coming out to be common, plus 1 plus H plus ion concentration by Ka. That implies S is equal to, this can be written as Ksp by S into 1 plus H plus concentration divided by Ka. So if I take that S to the other side, I'll get S square is equal to Ksp into 1 plus H plus ion concentration upon Ka value. So therefore, solubility in a buffer solution, directly you can use it like a formula. This is already derived in NCRT also. So I would suggest you directly use this formula in case if it is coming in exam. Got it? So this is the formula I would recommend you to remember directly. So whenever there is a buffer solution given, right? So we can directly use this as the solubility factor. Everyone, please go through it once. If there is any doubt, you can ask me again. Right. So the last thing what we need to know from here is that in case any of this kind of example is given for a buffer cases, how do we solve it? Okay. Or instead of buffer, the idea will be very similar, but this time it is given as complexation, right? So let me show you complexation cases. Complexation cases means we need to find the solubility of AgCl when you know uh, 4 moles of when 4 moles of NH3 is added to the aqueous solution. Now, in that case, what we need to do? Check. Suppose if you have an AgCl solid, you know that it will ionize into Ag plus aqueous plus Cl minus aqueous. But at the same time, due to the presence of ammonia, now what is happening is Ag plus aqueous plus 2 moles of NH3 aqueous, it would convert into a complex form. So that is NH3 twice and plus. Due to complexation, the solubility increases. Okay. So for this one, we write it as case P. While for the second case, this is called, you know, K complexation. K complexation. So now you will add these two. So then you will get this as AgCl plus 2 moles of NH3 aqueous, 2 moles of NH3 aqueous. That will be in equilibrium with Ag NH3 twice plus Cl minus. This is what you would have. Okay. So this will be the new. This will be the new solubility product. So therefore, this is the new solubility, correct? Because these two concentrations will be almost the same. So what? Why will that be same? See, out of this 4 moles, some 2s moles will be consumed here, and that will give you this much amount of solubility in both the cases. So therefore, A nu will be equal to S nu square by 4 minus 2 S nu whole square. But remember, S nu usually will be far, far smaller than the value of 4. I mean, 4, I'm writing it as a moles. Basically, it should be in 1 liter, okay? Added in 1 to 1 liter of solution so that the concentration remains 4 only, okay? And therefore, you can ignore that 2s. So therefore, S nu square will be equal to K nu. K nu value is actually Ksp into K complexing form, that multiplied by 4 square. So therefore, S nu is equal to 4 times of under root of Ksp into K complexation. This is what you would use. In major cases, this is the approximation which you will use directly. Okay. Now, same logic earlier, instead of, let's say, ammonia, I have H plus. So now what will happen if you had a cyanide plus H plus react into formation of that HCN. So you write the same way here, write this as S square. From H plus concentration, remove some amount here. And again, write the K nu formula, calculate the new solubility. Okay. So the type is very, very similar. Got it? See, you should always judge how much is the K nu value, because K nu value is Ksp into Kcom. Ksp is a very, very low value. Usually it will be in the range of 10 raised to power of minus 10. While complexation will be very high value, it will be in the range of 25, 10 raised to power of 25 and above, like this. So obviously this K nu will be a very high value. But it is not in all the cases. In some cases, right, you will notice that the complexation value is not that high. So in such case, do not ignore this S nu. That means you have to solve it like a quadratic equation completely, or you can just take the root here and then solve it for S nu again. Okay, clear everybody? Once. Okay, any doubt here?